Our sugary, sweet journey into the structure of sugars continues. What we're going to look at right now are different displays or projections that are commonly used for sugars. Sugars we've previously talked about, we've looked at them primarily in their linear form, so kind of straight up and down. That's known as a Fisher projection. We also look at sugars in a little bit more of a biologically relevant form. That biologically relevant form is known as the Hayworth projection. Now, there's a couple of things that I want you to recognize, and to give you some context, I'm going to draw glucose alongside this, or the linear form of glucose alongside this, so you can get kind of a frame of reference. Now, before I do that, what I want you to look at is this on the left-hand side is glucose. This is the um, cyclic form of glucose. That cyclic form of the sugar is commonly known as a Hayworth projection. Now, a Hayworth projection, there's a couple of things that I want you to recognize about this. Well, starting on the right-hand side, that's carbon number one. That might seem a little bit odd, um, just because, well, hey, what did carbon number one look like whenever we had a linear form of glucose? It looked like that. Now, this carbon right here, I'm going to put a little star by, as decent of a star that I can come up with. This is carbon number one, and it is now a chiral center because it is bound to one, two, three, and then what's not shown here is our H, four different things. So it is a chiral center. When it's in its linear form, it's bound to one, two, three things. So it is not a chiral center. This is an anomeric carbon, and that is a new chiral center. So a new chiral center, or newly formed chiral center, formed when cyclizing a linear sugar is known as the anomeric carbon. All right. Now, the next carbon, carbon number two, looks like this. Hey, how about that? Check. Now, what we want to be able to do is convert from this right here. Like, how do we convert from this to this? Well, if something is shown, we're going to use kind of our axis or equator as that right there. And that's kind of intentionally not drawn in a straight line. But I'm going to use this to indicate up or down. So if something is projected upward, like this or this, well, then we are going to draw it on the left-hand side of our linear molecule. Now, if something is shown on the right-hand side, or sorry, is shown downward from our ring, it's going to translate to being on the right-hand side. So carbon number two has an OH on the right-hand side because in its cyclic form, it has it going down. Carbon number three, right here. Well, that is going up, so that is going to be on the left-hand side. Carbon number four, right here. Well, that is going down, so it is on the right-hand side. Carbon number five. Oh man, I don't see an OH there. What gives? Well, we'll talk about this a little bit when we look at cyclization, but this right here is this OH. And if you remember, whenever we're looking at a linear form of a sugar, our highest numbered chiral carbon, which carbon number five is, our highest numbered chiral carbon will designate if we're talking about a D or L sugar. And the most biologically relevant form of glucose is our D sugar. So I'm going to draw that OH group on the right-hand side of my molecule. So this right here is linear glucose. This is also known as the Hayworth projection. Or sorry, the linear form is known as the Fisher projection. One of the keys is if it's on the right-hand side of the linear molecule, it's going to be down in the ring. If it's down in the ring, then it's going to be on the right-hand side. If it's up relative to the ring, then it's going to be on the left-hand side of my structure. So this is glucose as a Hayworth projection, and just what we drew, here is glucose as a Fisher projection. Now, one of the things that might seem a little bit odd is, wait a minute, Our anomeric carbon has an OH group. What gives? Here's your OH group. Whenever you make this carbon an anomeric carbon, this becomes an OH group rather than remaining as a carbonyl. So there's our Fisher projection and our Fisher and our Haworth projections of glucose. I want to show you two other sugars. They are ribose and fructose. Now, ribose is a sugar that you maybe have a little bit of familiarity with respect to ribose as a part of like deoxyribonucleic acid, if you've taken a biology class. Uh, but if you haven't, then you might not have that context. Now, ribose is kind of a simple sugar. It's one, two, three, four, five. What we're going to do is we're going to draw D-ribose. So what that means is our highest number. Oh, sorry. Let me go back a second. It is a pentamer, or pentose. Ribose is also an aldose. So what we know is it's an aldopentose. As an aldose, carbon number one has an aldehyde functional group. Carbon number six, just like all of our sugars, in the linear form, CH2OH. Now, this is a D sugar, so what that means is our highest numbered chiral carbon, which is going to be carbon number four, will have a hydroxide group on the right-hand side, a hydrogen on the left-hand side. Now, ribose, like I said, is kind of simple because of the fact that, well, we're just going to draw all of these OH groups on the right. I think that it's helpful to kind of keep these in mind and remember them for that reason, and remember the structure of ribose. But yeah, that's all there is to it. Now, with respect to, so this is our Fisher projection. This is our Haworth projection. Our Haworth projection is going to make a five-membered ring. One of those members is going to be oxygen. Now, carbon number one is right here. This is our anomeric carbon. This is carbon number one, where I just put a dot. So I have these two red dots by the carbon that is an anomeric carbon whenever it's in a ring, and one that becomes the anomeric carbon when it's in the linear form. What I've got an OH group coming off of this. Where is that OH group? Well, that is that carbonyl oxygen. But what are the other things that this is bound to? Well, that's one thing, two, three, and then four is going to be that oxygen. So this also has a hydrogen. So there's the four things that this anomeric carbon is kind of pointing out to. Now, carbon number two, I'm going to number it, three, four, and last but not least is CH2OH, five. Carbon number two, I need to account for that. Well, and I'm going to erase some of my other markings. Carbon number two, where is my OH group? Well, it's on the right-hand side of my linear form. Carbon number three has a hydroxide group on the right-hand side. So those are going to be OH and OH. Carbon number four, which is this carbon right here, where's that OH group? Oh, it doesn't have one because, and I'm going to switch colors to highlight this. That's carbon number four, and it's oxygen that basically came from its OH group. Okay, so that is our Haworth projection for our ribose. Now, what I'd like to show you is fructose. Fructose is sometimes referred to, I would say commonly, is commonly referred to as the ketose version of glucose. Now, a good question for that is, what does that mean? Well, let's think about what glucose is. Glucose is a hexose. And this is the ketose version of glucose. So this is a keto hexose. Okay, so we can start out by drawing one, two, three, four, five, six. What we know about our sixth carbon is it's going to have this CH2OH. We also know that carbon number one is going to be CH2OH. And carbon number two is going to have our carbonyl oxygen. So effectively, that accounts for three of the carbons and where their different groups are. Now, this leaves behind carbons number three, four, and five. If I told you, and again, by default, I want you to operate under the idea that you're drawing a D sugar. So what that means is carbon number five here has an OH group. Okay, so there is a D ketohexose. Have I defined it as being glucose quite yet? Or sorry, as fructose yet? I have not. I haven't added enough detail with these two carbons right here to show that yes, indeed, this is a ketohexose. Or sorry, this is fructose. Now I'm going to jump back and show you glucose again. One of the things that I always do whenever it comes to the linear form of glucose is when I hear glucose, my mind goes right, left, right. Because these three carbons, carbons number two, three, and four, those are the ones that define glucose. Similarly, two, three, and four, whenever somebody says, oh, cyclic glucose, what goes to my mind is down, up, down. I have this pattern. Now, why do I have that pattern? Why doesn't it extend to, well, this carbon right here? The reason it doesn't extend to that carbon is because this OH group, being on the right-hand side of my molecule, makes this a D sugar. So what that means is if I'm drawing a D ketohexose, which I've accounted for by positioning this OH group, and then I say, oh, well, I'm drawing the ketose version of glucose. Well, if I'm drawing glucose, it should be right, left, right for my OH groups. Well, I can't really do that on carbon number two, but can I, because I already have my carbonyl oxygen, that kind of supersedes it supersedes the nomenclature for glucose. But can I put an OH group on carbon number three? Yeah. Can I put an OH group on carbon number four? Yeah. Have I just drawn fructose, D fructose? Yeah, I have. It's great. Now, the Hayworth projection. So this is Fisher. This is the Hayworth. I have a nephew who's two, and his name is Fisher. Not sure if it has to do with sugar structures. In fact, I know it doesn't. I think it has to do with birds. At any rate, now I'm going to draw fructose. Fructose likes to form a five-membered ring. There's my five-membered ring. It's a four-carbon, five-membered ring. One member is oxygen. Now, carbon number six is going to be up here. Carbon number one is going to be up here. This is, and I'm going to switch colors for this. One, two, three, four, five, six. So those are my carbons. Now, next up is, well, carbon number two. What's that got? This is carbon number one. Done. Carbon number two. Well, that is going to be this, just like whenever we cyclize the aldohexose or sorry, any aldose, this carbonyl oxygen becomes an OH group. Well, this carbonyl oxygen is going to become an OH group on carbon number two. So it's there. Carbon number three, that is on the left-hand side of my structure, it's going up. Carbon number four, on the right-hand side of my structure, it's going down. Carbon number five, this oxygen is this oxygen. I'm going to put a little star to indicate that that is the same oxygen. Carbon number six is right here, and we are done. There's our Hayworth projection. There's our Fisher projection of each of these two sugars. Now, I hope that was helpful. I'm going to erase some of my markings so that you have a less busy representation. I'm also going to highlight the carbon and oxygen that become the carbon and oxygen. There's carbon 5 in the OH group, and the oxygen that becomes a part of the ring is highlighted there. Okay, well, I hope that was helpful, and I'll see you in the next video.